Hi everybody, it's me, Frederi. I'm back with one more video for you all. I was hoping to send this a few days earlier than today, but it is what it is. And when we get to Abuja, I can tell you more about the things that get in the way of professional commitment sometimes for me. So I'm still at my farm in Michigan. The topic of this video, which you should watch between the two videos that Dr. Catherine recorded, the topic is an explicit resolution for linear Bayesian analysis. We've already talked about Quadri's example where he wants to set up a test for whether a field has deficient nitrogen levels, uh, given the fact that there is a way of determining the true deficiency and how it relates to the test. Well, in this case, we're going to take the same idea again, but we're going to um, use continuous variables instead of yes/no type variables. So it's not going to be whether there's nitrogen deficiency in the field or not. It's going to be the true level of nitrogen in the field. That'll be the variable x that we're trying to emulate. And the variable y that we're going to use to emulate the variable x is the value of a nitrogen test. And so the idea here is that experimentalists can use expensive methods to determine the true value of X, the true level of nitrogen in the field. But academics and extension and agricultural extension agents, they want to design a much less expensive test to estimate the value of X. So it's a quantitative test. And so we're trying to have a much cheaper way of estimating X. And the estimate we're going to get is Y, which is also going to be a continuous variable. So what we will do is assume that there's a linear relationship between X and Y. And for this presentation, we're going to try to do things in as simple a way as possible. We're going to say, okay, if there's a linear relationship between x and y, that means that the relation that relates x and y is a linear function. And so y is going to be equal to beta times x. And that's like the simplest possible way of relating x and y in a linear manner. But because this is only statistically true, we're going to add an error term. And I have it written here as a sigma times epsilon. Epsilon is going to be a random term, which is a standard normal. So we'll talk during the workshop, we'll talk more about how to define this type of object, the standard normal random term, a standard normal random variable. And this value sigma is going to be the intensity of this error. Some people call this a noise, other people call it an error. And sigma would be the standard deviation of the level of error, the level of noise, because the standard deviation of epsilon itself is going to be 1 since it's been chosen to be standard normal. So for this quick example, we're assuming in particular that sigma is known, x and y have been gathered. This is part of our data. And we also know that if epsilon is a normal variable, its probability density has the form here at the bottom of the screen. It looks like there's some additional little bit of writing here on the edge of this page, but you can ignore these little things right here. So this expression here is the well-known density of this normal variable with mean zero and standard deviation sigma. So that's the density of the variable sigma times epsilon. All right, with all that said, so again, this is just a quick overview as a video. Some of you have already seen what a standard normal variable looks like. Others have not. We will go through this in more detail during the workshop. So here we are again with our linear model. The variable that we're able to measure ourselves is equal to beta times the actual value of the nitrogen level in the field, and there's a statistical error between these two variables. They're related in a linear way. Y is equal to beta times x plus statistical error. And what we want to do is we want to estimate beta so that we can figure out how the test responds to the actual level x. And in frequentist statistics, there's a method called least squares, LS, which gives us an estimator for beta, which is this expression over here. I'm using matrix notation here because presumably there's a bunch of different data points x, each of which corresponds to a different data point y. And then you can write these things in matrix notation. But for the purpose of this presentation, you can also just assume that there's a single value x, which is our data point, and a single value y, just to make the mathematics a little bit easier. But if there were a whole bunch of values, then this gives you the least squares estimate for beta. And people usually call that beta hat. Well, we want to ignore this frequentist estimate for beta, because what happens typically is that it's going to underestimate uncertainty. in how sure we are about what the value of beta is. So this value of beta hat doesn't contain any uncertainty. So if for those of you who know a little bit more of a statistical theory, you can build uncertainty into this estimator by assuming that, for example, um, the capital X have a certain distribution or capital Y have a certain distribution, and then that's going to transfer over to the uncertainty for beta hat. But even this is typically underestimated. And in Bayesian stat, we don't have to use a least squares estimator like this. We can let Bayes' theorem tell us everything without doing any computations ahead of time. And the difference between frequentist stat, where this is just the answer to the question, what's beta? In Bayesian stat, we have to have a little bit more information about beta at the prior level. So we talked about priors in the case where we were looking at the example that Quadri had set up. Well, here, because we're dealing with variables which can take any sort of value, these are variables with densities, we're going to make an assumption about beta, which is that beta is going to be normal itself, and it's going to have a prior standard deviation little s, so its variance, its prior variance will be sigma. So the capital N here means normal. Zero means that the mean of that normal variable is zero, so we don't know a priori whether beta is leaning more to the left or to the right. I will be drawing pictures during the workshop to explain all this a little bit more, but for the purpose of this quick video, we are setting at the prior level that beta is normal with mean zero and standard deviation s or variance s squared. And so sometimes people talk about the precision, the prior precision. The definition of precision when you're dealing with a single number is the inverse of variance. And so 1 over s squared is the prior precision on beta. And we can, of course, since this is still normal, using the formula that was at the bottom of the previous page, we also get that the density, the probability density for beta under this prior probability density looks just like this. It's exactly the same form that was at the top of the previous page, except here the variance is s squared rather than sigma squared. But it's the same expression because it's the same type of distribution. And so this is what we need to get started with Bayes. The second thing we need is a likelihood. Well, our linear model is the likelihood that we're going to use in Bayes. So this is the likelihood equation. And therefore, if you look at the density of the likelihood of the random variable y, given everything else, so we're assuming that sigma is known, we're assuming that x is known, we're assuming that epsilon is unknown but is normal and it's independent of everything else, and we're trying to figure out what beta is. But assuming that beta is known, then we immediately get that y, given beta x and sigma, is also going to be normal. Its mean will be equal to beta x, and its variance will be equal to sigma squared because of this additional error term right here. So this is going quickly because this is video. Some of you have already seen this sort of thing before, but this box here tells us that if our likelihood equation is this linear model, then our likelihood density is written like this, where we have a normal density, and by capital N, I still mean the same sort of thing as what we had in the previous line, or at the bottom of the previous slide here for those types of densities. So the likelihood density of y given everything else is normal with mean beta x and variance sigma squared. And again, for the purpose of this presentation, we will now assume, just for the purpose of this little 10-minute or 15-minute presentation, we'll assume that x and y are scalars. It's going to make our calculations a little easier to follow. Of course, normally you'd have a bunch of different pairs of x, y. Those are all your different data points. Here, we're assuming that there's only one pair of data points, just for the math. And what does Bayes' theorem for densities tell us? Bayes' theorem for densities tells us that the posterior density of beta, given everything that we're allowed to access, in this case, x, y, and the value sigma, which I'm assuming is known here, that posterior density is proportional to the product of the prior density for beta and the likelihood for y given beta. So the likelihood for y given beta looked like it was giving us y when beta was known, but it's still a formula, and you use that formula as a function of beta multiplied by this prior density for beta, and this gives you an expression which involves beta. So that's going to be a density for beta itself. It's going to tell us the distribution of beta. This symbol in the middle here is the proportionality sign. There will be a constant which does not depend on beta, but it depends on everything else in order to make this product a probability density. We don't need to keep track of it because we just need to recognize the form of the density when we make this product like this. The normalizing constant which is missing from this to make this an equal sign rather than a proportionality sign That missing constant, we don't really know what it is. It's actually the integral of all these, of this product here over all the values of beta, but it doesn't really matter. It could be very complicated. It doesn't matter because we will be able to recognize the density, the posterior density for beta by just doing some math on this product. So, as I said, we can ignore any multiplicative constants that do not involve beta. It'll be enough to just keep track of beta. So let's do the math with this. So this is slide number 3 of 4. Let's do the math. We want to do the math to figure out what this product is, see if we can recognize the true nature of the density of beta at the posterior level, which is our estimator for beta. It's a full distribution. And so when we write down Bayes' theorem, it tells us take the prior on beta, multiply it by the density of y at the prior level. So prior on beta, we said it was already this. We said that y was normal with this mean and this variance. So this is its density. There's some constants missing in front here, but they don't depend on beta, so I can just ignore them. And now we're ready to do a little calculation to try to recognize what kind of density this is as a function of beta. The first thing you would do is expand this square. So you get a beta squared. So when you expand the square, you see there's a -1/2 here that's going to be able to factor everything. And so here it is there. And then I have my beta squared over s squared, which is right here. So this term here transfers over here. And then I have to write out what these terms are. Well, the first one is going to be beta squared x squared over sigma squared. And then I'll have a double product, 2xy beta, and then the square of y divided by sigma squared. So when you expand this square here, it gives you these three terms, plus there's this term which came from the beginning. Now, since we're only interested in the behavior of this posterior density with respect to beta as a function of beta only, since this term does not involve a beta and it's inside an exponential, I can treat it as a constant factor, and so I can just ignore it. And that's how I go from this line to the next line where I've just deleted this term because this next line is proportional to the previous line. So if you remember a little bit about how your algebra works with powers and with exponentials, you'll see that I can go from here to there by ignoring this last term because it does not involve beta. Again, during the workshop, we'll go through this a little bit more carefully, but this is just a quick video so you can see what's going on. And then the next thing I do is I factor beta squared and see what goes next to it. So there's a beta squared here and there's a beta squared there. When I factor beta squared, I end up with this expression. And then the only thing that's left over, this -2xy beta, which I repeated over here. And now the next step is to do a so-called completion of the square. We're going to complete the square because anything that starts with something times beta squared minus beta times something else is the beginning of the expansion of a square. And so completing the square means trying to write this as a perfect square where there's maybe a term missing. The first thing I will do is I will factor out this term that's in front of beta squared. And when I do that, it goes to the denominator of the next term because it was missing there. So this step to this step, if you want to pause the video and see that you agree with what I wrote, it's just a little trick in order to get a leading term of beta squared by itself. And then when you have a term like this, which starts with beta squared minus 2 times something times beta, that's the beginning of this perfect square here. What's missing is the square of this last term, but since it doesn't involve beta, I can just ignore it and write this proportionality sign over here. So what I encourage you all is to see if you can actually, it's not really that there's any missing steps. What it is more is that I didn't write every little explanatory detail on the slide because it would get too wordy. There's no missing steps, but if you go through this yourselves with the video in hand and maybe a pen and paper, you can maybe spend half an hour to convince yourself that all this is correct. Each time I have a proportionality sign like this, it means that I've ignored a term which is a factor and which does not depend on beta. In this case, the factor that I've ignored is what you would get when you expand this square, when you have the square of this term here where there's no beta. And so therefore, finally, I remind everybody that what we're doing here is computing the posterior density of beta using Bayes' rule. And so as a function of beta, what we see is that this posterior density has to be a normal density because it's the exponential of negative some number times the square of something else, where the beta is here and then there's a minus sign. So what comes after the beta is really the mean value. And the variance is going to be the inverse of this term here, which is this term here in front is the inverse of the variance from that normal, which would be the precision. And so we're done, really. We recognize just by looking at this formula that the posterior density of beta is normal because of the form that it takes. There's a beta minus something to the power 2, and then there's multiplied by something else. So that's a normal density. All of that is inside an e to the power negative 1/2 times all that. So it is a normal density. The mean is whatever comes after the minus sign next to the beta here inside the square. So this is the mean. This is the posterior mean. And the posterior variance is the inverse of the posterior precision. So 1 over the term in front of this whole expression here. And so that's it. We're done. We have proved by hand, without doing any complicated integration or any math at all, really, just some very simple algebra. We've proved by hand that if you start with a prior on beta, which is normal, then you're going to get a posterior mean. So if you start with a prior on beta, which is normal with mean 0, then your posterior mean will have this form where sigma squared is the intensity of the noise in the likelihood model, and where S squared is the variance of your prior on beta. And we also proved here that the posterior variance of beta is 1 over the sum of these two precisions. So you have 1 over S squared, which is the precision of the prior for beta. We have x squared over sigma squared, which is a term coming from the likelihood. It's also the form of a precision. You add these two precisions together, that gives you another precision. If you want to write it as a variance, you do 1 over that. So the posterior variance for beta is this expression here, and we're happy because we are done actually using Bayes for this particular setup. Again, here I have, oops, at the bottom of this slide, the posterior precision is the inverse of the posterior variance, so it's the sum of these two terms. And one thing that's interesting here, I want to point out that th this posterior precision is actually, number one, it's always larger than the prior precision because x squared and sigma squared are positive. So the posterior precision is always bigger than 1 over s squared, which is the prior precision on beta. So there's always an improvement on your using this very simple setup. We can see there's always an improvement on how sure we are about beta itself. We start with a certain prior. Its precision is 1 over s squared. The posterior precision is larger, so there's better information after we use Bayes, even if there's just one single data point. And it's also larger. It gets larger as sigma gets smaller. So sigma gets smaller means there's higher precision in the likelihoods story. The smaller sigma is, if I go back real quick here for the likelihood equation, the smaller sigma is, the smaller this error term is in the likelihood equation. So the smaller the sigma, the better our modeling is relating x and y linearly to each other. And then the smaller sigma is, the larger this term is, the larger this term is, so the higher the precision. So small sigma is better because we get higher precision. You could also say the same thing with S squared. The more confident we are about beta at the prior level, the smaller S will be, and the larger this precision 1 over S squared will be. So same phenomenon there. It's just that you start with this precision, then you add something else, you get a better precision, and then that gets better and better the smaller sigma squared is. So this always all makes sense. And as I said, the posterior precision is always larger than the prior precision because you add this term here. And then just this is the last slide. So just one more thing. A similar calculation works out for the posterior density of sigma squared, assuming that beta is known and assuming that the prior on sigma squared is in the so-called inverse gamma distribution class. So what we're saying here is that there's two calculations that can be done by hand using linear models and Bayes. One is the one that we just did here, where we assume that everything is known except for beta, and then we can assume a normal prior on beta, and we get this explicit normal posterior with this normal posterior mean and this normal posterior variance. And beta remains normal at the posterior level, so that's the one thing that we just did. But you can do something similar for assuming that beta is known and sigma squared is unknown, using this inverse gamma distribution for the prior level. And in that case, the posterior density of sigma squared is also inverse gamma, with typically a higher precision than the prior precision on sigma squared. Now, the math here is a little bit more complicated, so that's why I didn't present it in this video, but you can find these things online. We will hopefully have a chance to look at how this works when we're in the workshop together, because it's good to see it once in your life at least. And so what we're saying here, just as a summary, we can do the math explicitly. If we know sigma squared, then we can estimate beta. Explicitly, we did it completely here. All the details are in this slide deck and in this video. If, on the other hand, we assume that beta is known, we can also estimate sigma squared. This is supposed to be sigma squared. 2 is kind of missing its bar here. If we assume that beta is known, we can estimate sigma squared by doing this assumption of an inverse gamma prior. And then if we don't know beta or sigma squared, then we can't really apply these two calculations directly. But what we can do, we can pretend like we know what they are and iterate the procedure when beta and sigma are both unknown. By doing this procedure, first trying to estimate beta, assuming sigma is known, then trying to estimate the resulting sigma, assuming that beta is known, but we can take for beta the one that we just created and sample from that. If we do this procedure iteratively, this is something which is known as the Gibbs sampler. If you look at Dr. Catherine's video, she talks about the Gibbs sampler. This is what it is for this linear system here, for this linear setup here. When you use the math that I talked about here and that I showed in full detail here for estimating beta and sigma squared, you do this math and you repeat the procedure over and over. This gives you the Gibbs sampler. And the Gibbs sampler is sometimes a very good and fast way computationally to get the joint posterior density of the pair beta sigma squared. You just repeat this procedure, let's say 10,000 times, and every time you sample, and then the set of the joint samples that you're going to get at the end are going to be very close to what you would get for the answer to the question of what Bayes should tell us when neither beta or sigma squared are known. The math behind that doesn't work out by hand. You can't figure it out. There's no nice formula, but using the skip sampling procedure, we get something which is very close. So we're very happy, and so this kind of explains a little bit of what's behind the scenes when you go from Dr. Catherine's first video about this sort of topic to her second video. This is kind of what's going on in between those two videos when you try to do some of the math by hand and you end up figuring that you had better do a type of method which is called Gibbs sampling. So thank you all very much for your attention, and I will stop this video and then check it to make sure it's good enough, and then send it out to everybody so you can all enjoy. Thank you. Bye. Looks like I might still be recording. I think I pressed the wrong button. Let me try to find the recording pause. Here it is. Pause recording. All right. Cheerio, everybody.